have served us well by reliably capturing business data over the last few decades. But in the age of internet and big data, it has reached its limit with respect to data scalability and quality. What if we can scale and distribute data freely without forming a pile of tightly coupled mess? And what if I tell you that your application is only capturing the tip of the iceberg and is capable of capturing much more data and insight? Well, welcome to the world of event sourcing. Event sourcing isn't just about storing data. It's about capturing the journey and the story behind every business interaction. It offers depth, richness, and tons of insight to be discovered. But it can also be used to make your architecture and systems more clean, decoupled, and adaptable to change. So dive with us as we unravel the world of event sourcing and discover how they're reshaping the way we think about data. Hi, I'm Stephen from Event Store. In this video, we'll first discuss the problems that event sourcing is trying to solve and the history behind it. And then, we'll unpack the concept of event sourcing and understand its contrast with traditional databases. Next, we'll dive into the core features of event sourcing and the key components that make it useful. And then finally, towards the end, we'll explore the core benefits of event sourcing, how it can drive insight and make your system more adaptable for this increasingly complex world. So without further ado, let's get right into it. So to understand where event sourcing stands in this huge landscape of databases, you first have to understand what it's trying to solve. In this segment, we'll first talk about why it's hard to manage complex and core business data. And then, we will talk about how traditional databases have historically been managing it, and the challenges that still exist up to this day. There are many kinds of data in this world, so some of them are simple, like the day of the week, maybe a street name, or the number of steps you walked today. And some are complex because it's volatile, it's frequently updated. It's also widely distributed to a diverse set of audiences and has to be compliant and follow business rules. There are many kinds of complex data in this world, but the ones that we're interested in is what we call core business data. Core business data often are complex, but it's extremely valuable to the business because it has to be used to improve its competitive advantage in the market. Some examples of core business data include things like a customer profile, their preferences, a patient's medical electronic health records, banking account and transactions, and things like sales transaction and agreements. The problem with core business data is that systems that processes them are often complex as well. They're not easy to understand and it's hard to change. Complex systems are hard to understand because it often involves many numbers of different systems or stakeholders. And they're often interconnected and interdependent as well too. Complex systems are hard to change because any change in this kind of system can cause a ripple effect that has huge impact across the entire ecosystem. In a world that is becoming more and more complex, this drives up the cost of managing core data, and this in turn hurts the business's capability to gather deeper insight and to adapt to an ever-changing market. And since databases are the primary storage of core business data, it plays a critical role in this problem. So let's talk about how a traditional database has historically been working with complex and core business data. So traditional databases such as relational has been the de facto database in the industry since it went mainstream in the 1990s. It was designed to provide transactional consistency across core business data, which works well for applications that typically have strict business rules. So an example of this is, say, like a wire transfer between two accounts. You won't want the bank to mess that up. So Transactional consistency ensures that a series of actions in a system are carried out completely and correctly, or just not at all. And this prevents the system from ending up in an unpredictable or erroneous state. And as a result, users can trust the system to maintain its integrity even after a lot of complicated actions. However, shortly after the internet went supernova in the early 2000s, developers discovered that it was hard to distribute data to more and more external systems. Well, this is because applications that use traditional database were primarily designed for transactional consistency. And transactional consistency doesn't really scale well, especially at that internet scale. There are a few reasons why that's the case, but we can boil it down to its problem when it comes to scaling it vertically and horizontally. Transactional consistency is hard to scale up because it requires you to upgrade the resources for one single server. So the CPU, memory, storage, network, and so on and so on. And since it gets progressively harder and harder to increase the resources for a single server, this means that there is an upper limit to how much it can actually vertically grow. And this can only be improved up to a certain point. Secondly, with only a single server managing your data, it also means that there is one single point of failure. And since database is a critical piece of infrastructure, when it fails, the entire system goes down with it. And lastly, it is also prone to concurrency issues when there is an increased amount of transactions. And this can cause race conditions, deadlocks, and other things that massively just slows down the database. And on the other hand, transactional consistency is also hard to scale out because it typically requires distributed transaction across multiple servers. And this slows due to latency and extra round trips that's required between the servers to make sure the change can be executed consistently across all of them. And finally, transactional consistency is also error prone because failure in any server will fail the transaction on all servers. And so as the number of participants increases, the risk of failure increases in a non-linear way as well. So as we see, transactional consistency is not really easy to scale up and out. But however, back in the days, developers continued to use it because there was just no better choice at that time. And this, along with the complexity of core business data, started to result in databases that were just huge, monolithic, tightly coupled to many parts of the system. And this brings us to the rise of eventual consistency in the 2010s. So with the popularity of cloud and big data in the 2010s, demand for data distribution continued to skyrocket. And because the scalability and decoupling issues that come with transactional consistency, many developers began to look for something else. And what they found were integration patterns that utilizes eventual consistency instead. Eventual consistency ensures that a system will become consistent over time given that no new updates are made. While users may see outdated data temporarily, the system guarantees that all systems will eventually converge into the same value. This may sound a little scary at first, but it actually allows the system to provide much higher scalability and looser coupling, even at the cost of immediate consistency. So we can compare transactional and eventual consistency in a few different ways. When it comes to transactional consistency, all the systems are either synchronized at once or not at all. Eventual consistency, on the other hand, promises that systems will be synchronized eventually. When it comes to coupling and scalability, transactionally consistent systems tend to be more tightly coupled. And this is because it requires all the system to immediately reflect changes. It makes them highly interdependent. And this interdependency means tighter coupling, since each system relies heavily on each other to function properly. This often leads to lower scalability as well too. And on the flip side, eventual consistency generally leads to systems that are more loosely coupled. And this is because systems are allowed to update at their own pace. And this approach fosters more independence between the systems, resulting in looser coupling as they don't need to coordinate instantly. And this makes eventual consistency much more easier to scale. To understand the difference between transactional and eventual consistency, we can also compare similar communication patterns. So for example, face-to-face communication can be compared to transactional consistency, where instant responses is required by multiple parties. So text messaging, on the other hand, is like eventual consistency because it doesn't need immediate response from everybody, and it's more hassle-free. Another way to describe transactional consistency is say that it's synchronous or two-way communication pattern, where eventual consistency is more like a asynchronous or one-way messaging pattern. And finally, when it comes to software development, transactional consistency often uses request-response type of communication protocol, where eventual consistency uses publish-subscribe more often. Now that we understand the difference between transactional and eventual consistency, let's take a look at how it evolved over time. So, eventual consistency is not a new concept. Scheduled jobs, ETLs have been popular since 1990s. However, there was a huge uptake of new event-driven solutions that supported eventual consistency during the 2000s and the 2010s. These tools include things like message queues, brokers, and practices like event-driven architecture. And these solutions help made it simpler for developers to implement event-driven applications. So while these solutions have been immensely helpful in advancement of eventual consistent operations, it still takes a lot of work and skills to develop fully decoupled and scalable systems. The common problem with these event-driven solutions is that they're still built on top of data that comes from traditional databases. Problems such as message duplications, message being out of order happens all the time in distributed systems and in the world of eventual consistency. And this is not trivial to handle, even with these newly developed event-driven solutions. A large part of this is caused by the fact that data is still captured in traditional databases, which doesn't have the proper features to support eventual consistency. Event sourcing and state transition databases, on the other hand, is designed with eventual consistency in mind, and it's the better alternative to decouple complex systems. We're going to explore more on this in the rest of the video. So before we dive deeper and talk about the features and benefits of event sourcing, let's first understand what sets event sourcing apart from traditional application patterns. So in this section, we'll talk about the key components and concepts of event sourcing and why these properties lead to a much richer data set. So data can arguably be represented in one of two ways: as a current state or a series of historical events. So, for example, your credit card account can be represented in its current state, with properties like account holder's name, a $0 balance, and a $1,000 credit limit. Or it can be represented as a series of historical events. So, for example, you opened an account, you bought a couple of stuff with the card, you paid off your credit card on time, and then your credit limit got upgraded. And even though these events individually doesn't resemble the current state, collectively together you can use it to build the same current state by replaying the events from start to finish. To compare the two, the current state representation is like a summary that's straightforward to understand. Historical events is like a story, on the other hand, that leads to a deeper insight. If the same logic is applied to databases, then traditional database is generally focused on capturing the current state. Event sourcing, however, uses what we call a state transition database, which is focused on capturing historical events into a log instead. So state transition database is a database that implements a log that captures a complete history of all events in an application. An event is an action that occurred which reveals the business intent behind it. The relationship between event sourcing and state transition database is simple. Event sourcing is an application pattern that uses a state transition database to store its data. Event sourcing is realized through code which saves events into a state transition database. So if you want to learn more about state transition database and the data model, just click on one of the links below. The state transition database is made up of two key concepts. First, the events, and then secondly, the log. Let's take a look at how these two concepts make event sourcing special and how it helps form its core features. So events are a much more granular way to represent your data. So again, event is something important that has occurred in the application. And every event has a name that represents the business action that took place. So for example, the credit card is open, got delivered, got activated, got suspended, was lost, and then so on and so on and so on. This is a very granular data representation that reveals the business intent behind each action. Traditional databases, on the other hand, don't often capture data at this kind of granularity because it is often optimized for a specific set of scenarios. So for example, it may only capture the open or closed events status because that might be enough for a particular high-level business report that the developers are working on. But the problem with this is that it loses the intentions and the interesting story behind. So we can say that the traditional data model is geared towards a set of specific reports, whereas the state transition data model is granular enough for any kind of foreseeable report. The log, on the other hand, captures and retains a complete history of all events. In contrast, traditional databases overrides data whenever something is changed or deleted. This makes the log a significantly more complete data model that stores all data from past to present. So, for example, the state transition database may store events for your credit card account. It has a complete record where it shows that you have opened an account, you've lost a credit card, and as a result, you canceled it. But for a traditional database, it only knows that the status of the account is closed. And the previous states are not kept or retained, and this makes traditional data model less comprehensive. So with both the granularity of events and the completeness of a log, this makes the state transition data model a much richer data model that gives extra depth and breadth to your data. This is like the difference between watching a high-definition video versus a grainy photo. One is just able to portray more data in more detail compared to the other. So now that we've gone through the two key concepts of the state transition database, namely the granularity of the events and two, the completeness of the log, we're ready to jump in and understand the core feature of event sourcing. So what the granularity and the completeness of the event log gives is the superior data flexibility and auditability that is unmatched with traditional databases. The state transition database gives you the flexibility to freely transform your data. This is like watching an entire TV series from start to finish, which allows you to see things from all sorts of different angles. Traditional database, on the other hand, is like you only watch the final episode of the final season, which gives you an extremely narrow point of view. The state transition database also gives you the auditability to make sure any interpretation of the data can actually be verified. Intuitively, when you have a complete log or journal of something, you can easily just flip through it and check whether someone's wild claims is actually correct. So maybe a sales manager claimed that your report that you produce have some critical bugs in there and demand an overnight fix. The auditability that comes with the event log can quickly tell you that your system is not broken, but instead someone on their team made an approved change that caused it. Using the state transition database is like being able to rewind and rewatch a certain scene in a TV series to settle a heated debate between you and your friend. The traditional database, on the contrary, is like cable TV, which only broadcasts the latest scene and is hard to travel back in time to review. So with this flexibility and auditability, the state transition database gives you a very special core feature, and it's the feature that allows you to generate virtually unlimited perspective across space and time while it's still true to the source. This feature leads to a few amazing benefits that are extremely useful for this increasingly complex world. Benefits that can help discover deeper insights for your business, and benefits that can help you decouple your systems so that it can be more adaptable. We're going to discuss more of this in the next section, but before we continue, let's summarize how we got here and what led to the core feature of event sourcing. So, first of all, the state transition database is a database that is used by the event sourcing application pattern. It is made up of a log that contains a sequence of named events. While the log itself contains the most complete history of change, named events are the most granular unit of change. Together, this forms a very rich data model that has both the flexibility to see from many different perspectives and also the auditability to verify these perspectives. And this, all in turn, leads to the core feature of event sourcing, which is the ability to reliably generate unlimited perspectives across space and time. So now that we've learned all this, let's go right into the core benefits of event sourcing and see how it helps to tackle complex systems. So state transition databases flexibility can clone your data into different forms that provide unique insight of your core business data. And this makes it simpler to understand complex systems so that the business can make more informed decisions. It also improves data quality and integrity since the completeness and auditability of the database can verify any downstream copy of your data, making it simpler to detect whether data is out of sync or corrupted. This is especially important in a data-driven world where big data analytics and machine learning are extremely vital to increase your competitive advantage. The insight can reveal patterns, trends, and anomalies that would otherwise be hard to detect in traditional systems. With a granular history of events, event sourcing can transform your data into different shapes and forms. For a credit card company, where all transactions are recorded, for example, different departments can construct their own customized report to gain extra insight. The product department can develop a custom report for, say, like top 10 retailers in Q4 so that they can develop partnerships with retailers to offer exclusive discounts. The cybersecurity team can query for suspicious overseas transactions to discover unusual purchasing patterns. The IT team can check the transaction throughput across time so that they can perform capacity planning of cloud resources. If the transactions were actually recorded in a version pre-optimized by one of these teams, then these kinds of transformations may not be possible. This is because some of the information required by other teams may have been collapsed into the current state. That wouldn't have been available unless the original events were retained. With a log that has the history of events, event sourcing can construct views from different timelines in the past, present, and future. The present state is usually rebuilt by replaying through all the relevant events in the log. The past, on the other hand, can be rebuilt by replaying events from the beginning up to a certain point in time. This can be done using temporal queries. Here are some examples of it. Point-in-time queries explores the data at a specific time. Range looks at data between the two dates. Duration examines the data within a period. Sequence queries for a specific sequence of events. And aggregation adds and summarizes a bunch of events together. And finally, data lineage examines the cause and effect of a specific event, which is useful for root cause analysis. These temporal queries are all helpful to better understand the past. Finally, while it's conventional to query the present state or past events, the future can be forecasted with machine learning and data analytics when there are a fair amount of events in your database. So event sourcing makes it easier for you to implement eventual consistent operations. Consequently, this helps you to decouple your system into smaller ones that are optimized for each use case. And at the end, this will lead to a more adaptable system that is less painful and costly to change. Let's see how this is achieved. As mentioned before, traditional databases tend to lead to tightly coupled systems due to its lack of support for eventual consistency. And as a result, you would often find your stack completely coupled to your database and schema. However, what most developers don't realize is that this kind of coupling is not limited to just the technical stack. The problem is also extended to the business stack as well, together as a solution stack. This form of coupling is generally not an issue for simple applications, but as the number of use cases increases over time, the stack will have to shoulder more responsibilities. And as you optimize the same stack for more and more use cases, issues starts to appear as it becomes overburdened. In this scenario, you may find business processes to be, say, overly complex and is frequently bottlenecked. Your code might be buggy or difficult to maintain. Data schema may require a lot of joins and contain many irrelevant columns. Your database may experience a lot of deadlocks or is often slow due to contention. And your servers seem to always be down during inconvenient hours and its resources are constantly depleted. These are some of the signs of tight coupling and an overburdened traditional database. So compared to traditional databases, event sourcing and state transition database can decouple these overburdened systems by providing better eventual consistency support. Since its event log has the auditability to verify whether copies of the data sent downstream are correct, it makes eventually consistent operations much easier to implement. For out-of-order messages, state transition database can help since events are always stored in the right order. And so applications can always retrieve sequence of events whenever it suspects the message arrived out of order. If message duplication is a problem when events are pushed, applications can choose to pull data from the state transition database where there are no duplications. Message loss can be detected by an application by comparing the event sequence number between its latest one and the one that just arrived. And when it's mismatched, it can request for the missing event directly from the database. Change data capture often creates messages that contains changes that are completely state-based, and this requires extrapolation or guesswork on the intention behind. Events, on the other hand, is recorded as business action, which has the granularity to reveal the intention behind. All these factors make it simpler for developers to implement eventually consistent operations, which makes it a breeze to decouple data from the complex solution stack. With event sourcing, you can build a state that is not tied to any existing data schema or database. In fact, because of this, you can build an entire solution stack that is optimized for one specific use case. For example, since you're not tied to a specific database, you can rebuild your data in a totally different database platform. Maybe with relational if you need the convenience and lower learning curve. Perhaps an analytical database or OLAP for analysis. A document database if you need to be scaled to a huge geographically distributed cluster. Or maybe an in-memory database for speed. Or even a graph database if you need to perform fast queries on nodes and edges. The point is, you can choose whatever database platform that suits your need, and you can also do the same in all the other layers in the stack. So instead of relying on the same old stack for every use case, you can now reconstruct highly optimized stack for each individual use case. For example, I can project my events to a database that is completely optimized for high read performance. I can use an in-memory database like Redis to store a copy of the data as cache. This cache can have a super simplified data schema that contains only one or two fields that I need for the fast read operation. The same can be done for another stack that is optimized for data analytics. Perhaps in this case, I would utilize an OLAP data cube that lets business analysts to slice data in multiple dimensions. This cube can be self-hosted on-premise to protect the data from malicious actors. So with all the options, the source of truth is not overburdened with all kinds of use cases and can freely delegate its responsibilities to other systems. This effectively decouples the source of truth from the other systems and allows developers to change the stack without causing a ripple effect on the whole system. And this makes the whole system more adaptable to change, which keeps the cost of managing core business data manageable, even as complexity increases. So core business data is expensive to manage because systems that use it are often interdependent and complex. Although traditional databases are popular, it is not a great choice for your core data, especially when it has to be distributed far and wide. This is because traditional databases often lead to overburdened and tightly coupled systems because it is designed for transactionally consistent operations. Event sourcing and state transition databases, on the other hand, is designed for consistent eventual consistency, which makes it easy to decouple complex systems. This reduces the burden on the database and allows optimized stack to be built for each individual use case. And additionally, it also allows data to be transformed into unlimited perspectives across space and time. All of this together makes State Transition Database the best database for this complex, event-driven, and data-driven world.